Welcome once again to the online lecture of Analytical Chemistry, B.Sc third year. In last lecture, we have learned about the application of spectroscopy from the first unit. In this lecture, we are going to learn about the second unit of this paper, number 12, that is H1 NMR spectroscopy. In this lecture, we are going to learn some little bit about the H1 NMR spectroscopy, that is theory and principle of the H1 NMR spectroscopy. The H1 NMR nothing but proton nuclear magnetic resonance spectroscopy, in which we are going to learn about the structural determination of the organic compound with the help of proton. So let's begin with the theory of H1 NMR spectroscopy. In this theory, we are going to learn the quantum description of this theory, how this H1 NMR, and nothing but that is what the proton NMR spectroscopy works. So the hydrogen nuclei, that is nothing but proton, rotates about an axis and thus have the property of spin. So it spins around its own axis due to the nuclear spin. The spin quantum number of the proton, that is I, is equal to half, that is plus or minus half. This is what the plus half is the nuclear spin of proton. So the angular momentum associated with the spin of the proton is quantized and have 2i plus 1 discrete states ranging from I minus 1, I minus 2 to I. When we place this proton in the magnetic field, this quantized energy levels discrete state was split up into plus I and minus I, that is nothing but plus half and minus half. Since the nucleus bears a charge, spin gives rise to a magnetic field. Due to what? The spinning of this nucleus, it generates the induced magnetic field. The resulting magnetic field mu is oriented along the axis of the spin and has a value that is characteristic for each type of proton. So it bears a definite magnetic moment. So the interrelation between proton spin and magnetic moment leads to a set of observable magnetic quantum state, that is m is equal to plus half and m is equal to minus half. So this splits into two magnetic quantum state, that is what magnetic quantum state, that is m plus half and m minus half, also called as a magnetic quantum numbers. This is small m is known as what the magnetic quantum number. These magnetic quantum states have equal energies in the absence of external field. When the field is 0, these m plus half and m minus half having the same energy. The proton possessing magnetic moment when brought into the influence of an external magnetic field becomes oriented such that its magnetic dipole, and hence the spin axis is parallel to the applied magnetic field. When we apply the external magnetic field to spinning proton, then the orientation of this proton changes and it what align uh, parallel to the applied magnetic field. Then the behavior of the proton is somewhat like that of a small bar magnet when introduced into the magnetic field. When we apply the external magnetic field to the bar magnet, then it what rotates uh, or aligns parallel to the applied magnetic fields as shown in here, as like this. See, This is a bar magnet, tiny bar magnet, and this is the applied external H0 is the external magnetic field. Then it's what aligns parallel to the that of external magnetic field. So proton, like this proton also aligns to the external magnetic field parallel to the what the external magnetic field. The potential energy of both the proton as well as that of the small bar magnet depends upon the orientation of the dipole with respect to the field. So it is depend upon the external magnetic field as well as the dipole with respect to the field. So the potential energy of the bar magnet can assume an infinite number of values depending upon its alignment and its given bar. So the change in energy when we apply the external magnetic field, then the energy is given what definite infinite number of the values depending upon alignment we have, that is what E is equal to minus mu z. Mu z is the what uh, magnetic moment, and H0 is the applied magnetic field. So this is the equation number 1, where mu z is the component of magnetic moment in the direction of an external field having a strength of H0. But in contrast, however, the potential energy of the proton is limited and have two discrete states corresponding to two magnetic quantum states, that is m plus half and m minus half. Then we have the limited potential energy, that is it is depending upon the magnetic moment, that is m, that is magnetic quantum number, that is plus half and minus half. So a vector product of this is what a this is nothing but mu z is the component of magnetic moment in the direction of an external magnetic field H0, and that mu is the what the magnetic moment, and I is the what the it is I is the nuclear spin, that is what the half, and m is the quantum number, magnetic quantum. See, this is what with the direction with magnetic field, that is applied magnetic field, is a plus half, and opposite to the magnetic field, that is what the minus half. So the potential energy of the spinning proton with the spin quantum number I and magnetic quantum number m in a magnetic field H0 is given by E is equal to minus m mu upon I beta H0 is the what equation when we place this proton in a external magnetic field, where beta is the what constant called as nuclear magneton, and mu is the magnetic moment along the spinning axis, and the proton and is expressed in the nuclear magneton. So what is the magnetic moment? Mu along with the spinning axis, and the proton and is expressed in the nuclear magneton, that is what the beta. For a proton with I is equal to half and m is equal to plus half, E1 is equal to minus that is nothing but mu beta H0, because I is equal to uh, I is equal to plus half. So and m is equal to what the plus half. So we have minus mu beta H0, that is equation number 3. For a proton with I is equal to half and m is equal to minus half, we will get the E2 is equal to plus mu beta H0. This is equation number 4. Then these two quantum energy corresponding to two possible orientation of the nuclear spin with respect to the magnetic field are shown below. How this uh, quantum number these two quantums energy corresponding to two possible orientation of the nuclear spin with respect to the magnetic field are shown when we apply the H0 or magnetic field. Then how this splits energy level splits, and how it shows the plus and minus orientation or uh, the clockwise and anti-clockwise orientation. That is nothing but delta E is equal to E2 minus E1, nothing but what, 2 mu beta H0. This is E2 plus mu beta H0 corresponds to m is equal to minus half, and E1, that is nothing but slower energy, minus beta H0, m is equal to plus half. So for the lower energy stage, that is m is equal to plus half, the vector of the magnetic moment is aligned with the field, and for the higher energy state, that is m is equal to minus half, the alignment is reverse. So what happens, see here, what the this uh, alignment of the nuclear spin is in the direction of H0, that is applied magnetic field. Then we have the equation, that is uh, m is equal to minus half and E2 is equal to plus mu beta. H0 is the higher energy states, and so energy increases, and here what the energy decreases when m is equal to plus half. So the energy difference between the two level is delta E is the energy difference, and is nothing but that is what E2 minus E1 is equal to 2 mu beta H0 is the equation number 5th. Then next, resonance condition. What is the resonance condition? The excitation from lower to higher nuclear magnetic quantum level can be brought about by absorption of the photons with energy h nu that just equal to that delta E. This is called the resonance condition. When the energy required to transition, when that what excitation from the lower to higher nuclear magnetic quantum number or quantum level can be brought about by absorption of the photon with energy h nu. When this radiation falls on this nuclei, then transition occur, and that nothing but that amount of energy required is nothing h nu is equal to that what the delta E. This is called the resonance condition. Thus for H1 and MR, delta E is equal to h nu is equal to what, 2 mu beta H0 is the resonance condition. The values of h nu lies in the RF range, that is radio frequency region. And then what is the frequency? That is what mu is nothing but 2 mu beta h0 upon h is called as the Lamers frequency. From the above equation, it follows that the frequency absorbed or emitted by a proton in moving from one energy level to the another is directly proportional to the applied magnetic field. This is the basis of H1NMR spectroscopy. What is the basics of H1NMR spectroscopy? From the above equation, it follows that the frequency absorbed or emitted by a proton in moving from one energy level to another is directly proportional to the applied magnetic field. Means frequency is directly proportional to that of the H0, whatever the energy, which is nothing but frequency, and which is equal to the applied magnetic field. And magnetic field, this is the what the basis of H1NMR spectroscopy. So distribution of proton between the magnetic quantum states. In the absence of magnetic field, the energy of the magnetic quantum states are identical. When you are not applying the magnetic field, the energy states are what, quantized, that is equal, identical. So consequently, a large assemblance of protons will contain an identical number of nuclei with m is equal to plus half and m is equal to minus half. When placed in the field, however, the nuclei tend to orient themselves so that the lower energy state, that is what the m plus half, predominates, because due to the what, applied magnetic field. and orientation of the nuclei. So, because the thermal energies of the room temperature are several orders of the magnitude greater than these magnetic energy differences. But because the thermal energies of the room temperatures are several orders of magnitude, so greater than these of the magnetic energy difference, so the thermal agitation tend to offset the magnetic effects, and only a minute excess, that is what the lower than 10 ppm of the nuclei persists in the lower energy state. The success of H1 NMR, however, depend upon this slight excess. If the number of protons in the two states were identical, the probability for the absorption of radiation would be the same as the probability for re-emission by the particles passing from the higher energy state to the lower energy state. Under these circumstances, the net absorption would be nil. What happen when what the same number of nuclei at the higher energy state and at the lower energy state? So there is a probability of the re-emission of the particle passing from the higher energy state to the lower energy state. So the in these circumstances the net absorption would be what? Nil, because it does not show the maximum or the absorption. That is what absorption is nil, because the uh, re-emission also takes place. So this is about the theory of H1 NMR spectroscopy. If you have any queries regarding this topic, please comment in the YouTube comment box. I will try to answer your question. Thank you. Thanks a lot.